Chapter 1, Exponential and Logistic Models, Part 1. Part 1, we're going to consider general introduction to exponential models, and Part 2, we'll move on to logistic models. Our basic exponential equation says I of t equals I0 e to the r sub e times t. That's an exponential growth equation. In this case, I0 is the initial infected population, and that's at t equals 0 days. R sub e, that's a subscript e, not the letter, not times e. R sub e is an exponential growth rate, and we'll talk about that more in a minute. T is equal to time in days. With an exponential model, t can be any time unit. But with the spread of a virus, we're usually talking about a time frame of several months. It makes sense to use days, but mathematically, we could use weeks, months, years. You could use millenniums if you wanted. It's just that you'd be dealing with a lot of weird scientific notation numbers. I of t is equal to the number of infections at time t, and E is actually equal to 2.718828 dot dot dot. It's this interesting number. It's both transcendental and irrational like pi. It seems like an odd number. As time goes on, we'll discuss a little bit more of it, but suffice it to say, it's the most important number in all of mathematics, and as students' math education continues, it becomes more and more front and center. In calculus, we'll use this number. Differential equations is used almost on a daily basis. In differential equations, we use that to model pretty much how the whole electrical and mechanical universe works. And this E shows up almost on a daily basis. So we're going to work with it in here, mainly to get pre-calculus students used to working with it and comfortable with it. We're going to start with a very simple problem. There are 10 infections initially, and the number of infections double every 3 days. This is what was happening with COVID back in the winter of 2020, or at least the positive tests were doubling every 3 days. Let's set up this model. Well, we have this model, I of t equals I0 e to the r sub e t. Setting up the model is largely finding these two parameters. If we can find these two numbers, we're all set, and we just fill in the blanks, and then we write the model out. We'll talk in the next chapter of what good the model is. Well, first of all, I0 is a number of initial infections. That's equal to 10, so we can identify I0 equals 10. And you can substitute back into the model. I of t is 10 e to the r e times t. And then next we're still left with this parameter right here. And the key to that's a growth rate. So to figure out how fast it's growing, we have to know what happens sometime in the future. Well, we know it doubles every 3 days. So what does that tell us? It says when t is equal to 3 days, I is equal to 10 doubled is 20. And we can also express that basic idea by saying I of 3 equals 20, but this is a little bit easier. Now we can substitute. 20 substitutes into here, 3 in here. We're left with one variable. And so we have 20 equals 10 e to the r e times 3. Now we need to solve for RE. Well, we can divide both sides by 10, and that gives us 2 equals e to the 3 RE. Yeah, and then we can get rid of this e by taking the natural log of both sides. Oops, my parentheses goes here. And then the ln and the e cancel, and we just have ln of 2 is equal to 3re. And then we can divide by 3, and we have re is equal to ln of 2 divided by 3. And we can approximate that on a calculator. We have approximately 231. And we can keep how many significant figures we need based on how accurate these numbers are here. And the chances are something won't exactly double every 3 days, so how certain you are up here would affect this, but that's another matter. We won't get into that. So in any event, we can rewrite our final model. I of t is equal to 10e to the 0.2, oops, 231t. And there is our exponential model. What good is it? Well, we can use it to predict the future. Given a time value, we can calculate and find the number of infections. Or, given a number of infections, we can figure out what time value will produce that. So the whole goal of a model for a pandemic is to figure out what's going to happen in the future so we can act accordingly. So this is the simplest model. Many of my friends and students have said, well, viruses spread exponentially. My answer is, well, sort of, but not quite. In the coming chapters, we'll learn why an exponential model is woefully inadequate. We'll replace it with something much better. So that's all for part 1.